The diode equation is just this. We can say it's also known as the Shockley equation. The diode current is equal to the scale current, IS, and that's something that's given to you by the factory that made it, or that you can measure, or you can calculate. And it's often very small. It's a tiny, tiny value. So that's scale current times e to the VD minus 1. Now note, this is not ID is equal to IS e to the VD over VT minus 1. It's not this. Never write it that way. If you do that, you'll really end up with lots of trouble. So that's the diode equation. And remember, the symbol for diode looks like this. It's a triangle facing a line, just helping give you some idea of the direction that the current flows and how we measure the voltage. So the standard is that the voltage is defined in this way, from plus to minus, and the current is measured flowing that way. It doesn't mean that the current or voltage can't be negative. It just means this is how we define positive and negative on that. And this number VT, a thermal voltage, is KT over Q, or about 0.0258 volts, or about 26 millivolts at room temperature. Now, usually the relations that we'll use for the diode current are these two. And because we have just the drain current and the diode current and the diode voltage are really the only two variables we have, we can write this equation either way. It is meaningful in both ways, whether we find the diode current based on what the diode voltage is, or the diode voltage based on what the diode current is. Either way, we can often forget about this minus 1. As long as we have VD is greater than about 0.25 volts. As long as we have a value greater than about that, we can just basically forget it. Now, VT does definitely depend on temperature. Oops, and as we change temperature, we get wild changes in the voltage that we would see, or the current or voltage that we would see. So if we had, if IS, the scale current is 1e to the minus 15 amps, and and you might be wondering if we use, or depending on what happens at some other temperatures, if we were at I is equal to, let's see, if we were at 200 degrees K, so that's cold, that's minus 70 degrees C, but it's still plausible as a temperature that a device might be expected to start working at. So, and if we had VD is equal to 0.7 volts, then what would the current be? So we'd have 1e to the minus 15. 0.7 volts means that we can use this equation times e to the 0.7, and if we find KT over Q at 200 degrees K, it's 0.017. And this equals 762 amps. That's a big current. It's cold, and we get a big current. if we changed to 500 degrees K, so that's 300 degrees warmer, 500 degrees K, that's like 150 degrees C or something like that. Then we have I is equal to 1e to the minus 15 times e to the 0.7. And now we would get a number of 0.043 for VT. And this, we'd now have 11.7 nanoamps, right? So 1e to the minus 9 amps. Right. So we've changed, what, 11 orders of magnitude between 200 degrees K, which is cold, and 500 degrees K, which is really hot. But we've changed an enormous number or an enormous change in current just by changing the temperature. So is that realistic? Well, if you think about what happens to a satellite orbiting the Earth, where it goes in and out of sunshine every 90 minutes, a satellite can easily experience this kind of change in temperature. 200 degrees to 500 degrees K every hour and a half, really every 45 minutes. So, or even less than that, I suppose, every 20 minutes, something like that. So it would be critical in the satellite to account for that in space and make sure that these variations in temperature either don't cause a problem or you keep the device heated up enough so that it doesn't have that kind of issue. It's an enormous effect that we have to be aware of. It doesn't make diodes and transistors useless, and every transistor has a couple of diodes in it, but it's something that we can't just ignore all of the time. Now, the diode voltage has a huge impact on the current that we get. And you could see that by understanding that the current, we take the natural log of the current, we have a direct influence on the voltage we see across it. So if I still use 1e to the minus 15 amps for the scale current at 0.7 volts and at room temperature, at VD is equal to 0.7 volts, we get ID is equal to 601 microamps. If we just increase this by 1 millivolt, 0.701 volts for VD, then ID is now equal to 631 microamps. That's a big change. We changed the voltage by 1 microvolt, and we caused a 30 microamp change in current. Those are really large, significant changes. If we went up to 0.71 volts, then the drain current is now 894 microamps. If this didn't seem like a big change, this surely must seem like a big change, 25% or something like that. It's a big effect, and it means if we're trying to control a diode to a certain specific voltage, then we need to have very good control of the. If we're trying to control a certain current out of a diode, we need to have very good control of the voltage. It does mean that if we can generate a steady current, then we could use a diode to generate a steady voltage. So if we can supply a steady current through a diode, then we can expect this voltage to be quite steady. And that is the basis of a regulator circuit that can be very useful. But these small changes in current, or these large changes in current for a small change in voltage can make it tough to, for instance, keep the diode from burning up or keep your LED from burning up, which is, after all, a diode. So if this diode was actually an LED, and if we want 15 milliamps, So then the voltage, let's see now. So if we have ID is equal to 15 milliamps, then VD, the diode voltage, by using this relation, we can find it. VD would be 0.783 volts. If we had 25 milliamps, then VD is 0.796 volts. That's not a large change in voltage. And we have to watch out for that. And the way to take care of that is we don't build a circuit like this. That's a symbol for a diode. I can't draw very well. Don't make it like this. That would be a bad idea, because any small variation in voltage, if 20 milliamps was the limit to load up, if we went from 0.783 to 0.796, we burned up our LED. So instead, always make a circuit that looks like this. We have a voltage, a power supply, and then we have a resistor to limit the current. And even if you're not making a diode or an LED, if you've got a diode in your circuit, you should do something like this. And you figure this resistance so that for the maximum voltage you could see, if it was, say, if you were using the power supply in the lab, the max voltage is 6 volts. And the current you want to limit it to is, say, 50 milliamps, then we can find a resistance, which would be 6 divided by 0.015, which would be 400 ohms. That would limit the current so that it's always less than 15 milliamps. Anything more will be absorbed in that resistor. But you can figure out the situation for whatever power supply and whatever situation you have. And you can also make use of the limits on the power supply, but those can be kind of too much of a broad, rough stroke that doesn't always really serve the purpose that you need. What if we had, if we applied a little bit more, right? What if we just accidentally, briefly, momentarily turned the knob in the power supply up from 0.7 up to 1.4, so we double the voltage, right? But this is an exponential thing. So now we have I, the diode current, is equal to 1e to the minus 15. And again, at 300 degrees K, 1.4 over 0.0258. This is equal to 1e to the minus 15 times 3.68 e to the 23. This got big, right? That got very big. And this would be 368 mega, not milli, mega amps. And if we look at how much is dissipated in the diode, that would be V diode times I diode. That's just the voltage and the current across the diode, what it has to be dissipating, 1.4 volts times 368 e to the 6 amps. And we get 515 megawatts. That's about the typical output of all of Colorado Springs utilities generators and their customer load, 500 megawatts. And that would be running through one diode that you just happen to turn up to 1.4 volts. Obviously, your diode wouldn't be able to carry a megawatt, let alone 500 megawatts, it would burn up. It'd be vaporized. Something inside it would have burned up long before you hit 1.4, and it would not take very long. So be really, really careful about limiting the current that you have in a diode with a resistor, and or using the limits in the power supplies. Like I say, that can be sometimes too broad and rough of a stroke. Sometimes you need to supply more current in certain places. So just diodes are wonderful devices. They're fabulously useful, but do be careful with them and do think about what you're doing in the lab, especially.